We are rounding the corner. Like we're almost done now with fundamentals, background of databases before we shift gears and get into other stuff. And that's going to be happening basically this week. Today, I'm hoping to wrap up the background, fundamentals, things that I hope you have in your head to put into context, stuff that's happening when you're dealing with databases. So today's the day when everything hopefully kind of comes together. We have been talking about um, data structures and algorithms, which uh, this class, I don't know, maybe this is the first time that you are experiencing a discussion about these two things. I've been trying my best to differentiate the two. Like that there's a thing called data structures, which is how you structure your data, and algorithms, which is how, given a certain input, or any inputs, you would produce a particular output. So for data structures, we've talked about arrays and trees. And for algorithms, mainly we've talked about search. Also, insertion and deletion. Those are also procedures that you can do. And those things take time. Algorithms are measured in time. Data structures are measured in space. And so these are two sort of different concepts that we're working with simultaneously. And where we're at right now, today, is on the data structures end, we're going to continue our discussions about both arrays and trees. And it gets a little confusing because it turns out that you can use an array to represent a tree. And an array and a tree are two very different things, kind of, except that you can have a tree and you can sort of shove it, you can encode it into an array. So although we're talking about arrays, depending on exactly how you do it, the array is also a tree. And we like trees. Trees, that data structure has a lot of benefits. The benefits are on the algorithm side, where you can search, insert, delete, all three of them efficiently. And so that's great. This algorithm or each of those three algorithms run or can be implemented very well on a tree data structure. And that's where we're at. So we're talking about a tree data structure encoded in an array, and search, insert, delete algorithms that are very good on an array when we combine them. So let me pause and ask you guys if there's anything that we've talked about previously or where you might suspect where we're going that you have questions about, and I can address those before getting into just new stuff. Silence. Okay, well then let's continue. All right. This first part of class, at least the way that I treat this particular class, um, to me feels a bit chaotic, and I don't know of a way to make it more kind of step by step. Let me preview really quick things that I've talked about in this session. Oh, this is good. Yeah. Index tables, blocks, hard drives, very good. All right. So, the reason why we're talking about arrays so much is because with actual hardware, stuff works like an array. All right. So like all of the data that you want to store, it's going to go on a hard drive. And there's another concept that we've been talking about, which is if you want to do something, could you waste a little bit of time in the beginning? Like you waste time, like sorting your data, for example. Like that takes time to do. Is it worth it? Well, if you sort everything one time, and that takes time, then now you have sorted data and you can do other stuff really quickly, over and over and over and over, like a search. So sometimes it can be worth it to waste a little bit of time in the beginning. Similarly, it can be worth it to waste a little bit of space. So here on the screen, on the left-hand side, is something called an index table. And the index table, this is really the data structure that you can use to quickly get to a part of the data that you care about. So the index table, first of all, it takes up more space. Like I drew a table here to the left. That's extra space that I'm taking up, in addition to the data that I'm storing. But also, that table takes time to build, the index table. So now we're not only wasting a little bit of time, but we're also taking up a little bit of space. And why do all of that? It's to make things go faster. So the data is going to be going on this, the hard drive. You turn off your computer, everything here is still there. Turn the computer back on, hey, the data's still there. So far, so good. Now, the index table is a separate piece of data that also goes on the hard drive. I mean, you turn the thing off, you turn a computer off, you hope to not lose anything, and so all of that's still on the hard drive. But now you boot up the computer, you start the computer, and you want to start searching through stuff on the hard drive. So you have an index table that's also on the hard drive that then gets copied to memory. So the index table is small. At least it can fit on memory. It's, it's at least that small. You can load it into your memory. And this, the hard drive, is like a million times, actually not like, it is a million times slower than your RAM. So you take time, a little tiny bit of space on your hard drive to, in addition to your data, you have something called an index table. And then once you turn the computer on, you copy that index table over to your million times faster RAM. And then you work from that using your data structure that you've spent time building. And now it's on your RAM, super fast. What do you want to find? What data do you want? Zip, zap, zoop, really quick. And then you can take the slow thing to actually pull the record from the disk. All right, so that's the way it goes. Okay, so we've been talking about trees, in particular binary trees. Binary trees are trees that any particular node can have two children, and not just two children, but for any node in the tree, children to the left are less than or equal to the parent, and everything to the right is strictly greater than the parent. And so that is what defines a binary tree. I've talked about a binary tree because it's the simplest kind of tree, and really all of the highlights of a binary tree as far as what it means to be balanced, what it means to be full, what it means to traverse a tree. You start at the root and you kind of go deep, deep, deep. The big factor in the tree is its depth, right? As opposed to an array where you care about length. For a tree, you care about depth. All of that is true for binary trees, and it's also true for other types of trees. Today we're going to be talking about other types of trees. The whole reason for talking about binary trees was to explain vocabulary and certain concepts that are true for all trees, but binary trees just happen to be a little bit simpler and hopefully in shorter time express these concepts. Assuming that you're now comfortable with binary trees, you can basically learn about any other tree, and it's not too hard. You just have to tweak something here or there. But all of the major concepts we've already covered. Let's go into it. I'll just go where I want to go. So we talked about binary trees, and in particular, not just binary trees, but balanced trees. Okay, a tree that is balanced is a tree that has a minimum depth. You can have some empty spaces and stuff in the bottom. It doesn't have to be full. But a balanced tree, you can't squish it. You can't make the depth any smaller. Like the depth is as shallow as it can be. And that is the property of being balanced. And you get benefits from that. In particular, when you have to start at the root and you need to go down, 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 down into the tree, if it's not very deep, then from the top to the bottom, it's not a long path, right? Or at least the path is as short as possible. So for the rest of today, we can only consider balanced trees, okay? There's other cases where the tree is not balanced and things don't work nicely and stuff like that, but we're past that. Right now, we're focused on the case when trees are balanced. And I'm going to introduce a tree called a B tree. So there's a B tree that I'll be talking about today, and also a B plus tree, which is basically a B tree with some extra little stuff. And the B plus tree is the crescendo of this part of the lecture, because in SQL, which is the database we'll be talking about and actually using in this course, uses a B plus tree in real life. Like this is the thing that's used. And why it's used and what exactly it is what we're going to cover. So don't be scared, all right? Like everything, I mean, we've already talked about binary trees. I'm just going to be adding in some like extra details, basically. But we've like this should be a little bit of a relaxing class because we're not going into anything that's conceptually difficult. We've already covered all of that. So let me just jump into it. Turn off my camera so you guys don't have to see my close-up face. There we go. All right. B tree. So I don't know where the name B comes from. I should probably look that up, but I don't know. It's a tree, and there's a few notable things about it. First of all, there's an extra parameter. If you're talking about a B tree, there's a parameter m. So n is usually for the number of nodes of a tree. Okay, so the letter n is reserved to talk about the number of nodes. So a nearby letter, m, is just used with practitioners to refer to the number of possible children of any node. Okay? Just for fun, and because I like the number and I think it gets all of the points across, I'm going to make m equal to 4. Okay, m can be 3, it can be 5, it can be 10, it can be 1,000. M can kind of be whatever number you want, depending on the circumstance. But for the purposes of this whiteboard kind of explanation, I'm choosing m to be the number 4. So what that means is that we have nodes and they can have 4 children, okay? 5, no good. M is not equal to 5. M is equal to 4. Can we have 3? Sometimes, yeah. This is still okay with m equals 4 because m is the number of possible children. Although there's 3 children now, it's possible that you could add another one, and so okay. M doesn't have to be 4, but like that's the maximum. You can't exceed it. All right. Now, with a binary tree, it's binary because you can break left or you can break right. You can go left or you can go right. And if this is some number x in this node, then you go left if the number that you care about is less than or equal to x. And if the number is greater than x, then you go to the right. All right, so that's what makes it a binary tree. This is a yes, no, one or the other kind of situation. But here, m is not equal to 2, m is equal to 4. So it's a little different than this, but it's basically the same thing. Let's say we have x, y, and z. So now a node can have up to a maximum of 3 values. Why 3? Well, if we were to write this on a number line, you'd have some number x, some number y, some number z, and there will be 4 regions. Here, which is less than equal to x. Here, this region, which is greater than x, but less than equal to y. this region, which is greater than y but less than or equal to z, and then this region, which is strictly greater than z. Okay, so we have 1, 2, 3 values that result in 4 different regions. Okay, so we could have a child here, that's one child, a child here, a child here, or a child here. Okay, so those are the 4 children. And let me erase this now. I'll just keep the less than equal to's, whatever. All right, there we go. So that is the way that we would traverse the tree. If the number is strictly less than or equal to x, you would go that way. If the number is between x and y, you would go to the second child. If the number is between y and z, you go to this third child. And if the number is strictly greater than z, then you go right. And that is the way a for tree works. All right, so again, nothing new. It's just a little tweak on things that we've talked about with a binary tree. Let me give a quick concrete example. I don't know, 5, 7, 10. 1, 2, 3, 4 children. Here, I will make it a full node. 2, 3, 4. Here, 6. Here, the number 7, 8, and here, 12, 13, 14. Okay, so this is the way that this type of tree would look, a B tree, where not just any B tree, but where m equals 4. I want to emphasize that it's okay to, this node here only has 1 value, right? Where this one here, that has 3 values. That's okay, no problem. This is balanced, not full. To be full, then this would have 3 values, this would have 3 values, and everything would have 3 values, but we don't need a tree to be full. The thing that we care about is the tree balanced? And this is a balanced tree. It is, it can be made no shallower. That's the definition that I like for balanced trees. The depth is as small as you can possibly make it. Now that has different, how to say, different trees can be balanced with a couple of extra notes. All right, it's balanced, but something, something. So here, this is a balanced tree. It's not full. I'm going to give another example of a balanced tree. This one. That's okay too. Actually, wait, hold on. Let me go back. Make sure I get this right. Back. Okay. This 6, 7, 8 there. Right. This is also a balanced tree. We can't make it any shallower. It's okay that there's a number missing here. That doesn't break anything, okay? This is still a balanced tree. Everything to the left is smaller than the number 5. Everything in this child is between the numbers 5 and 10. Everything in this child is strictly greater than 10. And it's fine. It's fine. This is a balanced tree. It does not matter in this case that there's a missing value where things above you can have empty spaces. Okay, no problem. Because if you're following the rules with not, I mean, here m is still equal to 4. Is there any way that we could take this tree and make it less deep? There is not. It is as shallow as it can be. Therefore, it's balanced and everything's good. Oh, what about 11 and 9? Between the 5 and 10. Sorry, maybe I'm missing something. Who's ever asking these questions? Would you mind unmuting yourself? What about 11? Right, okay. So okay, because you're not unmuting yourself, I have to sort of guess. What if we were to insert the number 11? Or what if we were to insert the number 9? We'll get to this, well, might as well get to it now. Let's say, oh, I gotta go back up here. So, a B tree has this number m, okay? You need to give the number m in addition to requesting a B tree. I want a B tree, but a B tree where m, in this case, equals 4. You could make m equal 5, 3, 1,000, different stuff. And for this lecture, m is 4. Another very important property, I'll put this sort of here like that. Those are the properties. This is built bottom up. Okay. This is a very important property of a B tree. It's being built bottom up. Turn on the camera here. All right. So what bottom up means is, like there's a tree. The root is at the top, and then you have the leaves at the bottom. And we're only concerned about balanced trees. Okay, I'm only going to repeat that so many times for the entirety of this lecture. With a B tree and a B plus tree and everything else, everything is balanced. Okay, we are maintaining balance. That when we insert something, the tree is built bottom up. What that means is that you start at the root and you want to insert something, and so you go down, 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 down to the bottom, insert the thing, and then if you've disrupted balance, well, then you fix it. And then there's an adjustment. So first you insert at the bottom, and if you've broken the balance, then there's an adjustment step. Okay. Now, another thing that I want to say for the B tree, I'll show, there's actually a really nice web app that goes through this. This is not an algorithms course. Okay. So I am not going to ask or even explain to you the specifics of how search, insertion, or delete work on a B tree. Okay, we've covered these for a binary tree. I hope that you're convinced kind of how these things go, but I'm not going to ask for the specifics of this more advanced type of tree from you. The only thing that I want you to know is that there's a way that it works and that the math all follows. for fast search, fast insert, fast delete. The details behind that, if you're interested in this stuff, good for you. I mean, hey, I'll take time, some office hours. I'll walk through it with you. You can look it up on Wikipedia or YouTube or whatever else. I'm not going to test you on this. I'm not going to have this as a part of the homework or anything like this. What I care about is the idea that every single one of you have an idea for how these things work. If you want to do the specifics, I encourage that. I'm not demanding it, okay? So for the B tree and for this lecture, I'm being a little bit hand-wavy about how these things go. I could be more specific, but this isn't a data structures class. This isn't an algorithms class. This is a class on data structures. So we're, at least what I'm teaching goes to a certain point, and after that, things get kind of hand-wavy, and yeah, I'm stopping there. Okay, that's my decision. That's how I'm teaching this class. So this is a very good question. Let's take this concrete tree and turn off my video here. What about inserting the number 9? What about inserting the number 11? Whoever asked this is fantastic. That, like, you have a very good way of thinking. Here's a concrete example. Let me just throw a wrench into how this works. Like, let me come up with a problem where to see how you get out of it. Let's do it. So we insert the number 9. Oh, okay. Well, we'll insert the number 11 because that was strictly asked first. And then we'll do, actually, I'll do the number 11, then I'll pick out on somebody for the number 9. Okay. Again, we're building this bottom up. So we want to insert 9. Bottom up means what it is. It goes at the bottom first. I'm sorry, I'm doing 11. All right, so we insert 11. All right, well, 11 is bigger than 10, so we branch right. Okay, now we're at the number 11, and we would like to put the number 11 here. Okay, that's kind of where it should go. But we can only have 3 values in a node, not 4. You can have 4 children, but you can only have 3 values because 3 values create 4 regions, and those regions are the children. Okay, so this is no good. This is a little bit wonky. All right, now the procedure is that you take one of the middle numbers and you make that a root, or you pull it out. One of the middle numbers. So in the same way where when we had a binary tree, you could go less than equal to strictly greater than, left, right, or you could do strictly less than and then greater than or equal to on the right. Doesn't matter so long you're consistent. This would be a right bias. And if we do this, that would be a left bias, right? So it doesn't matter. It's all the same. You have to choose either left or right. Doesn't matter. Just be consistent. So the same thing here. We have 2 middle values, and if we prefer this one, that's going to be called a left bias, right? So we choose, if there's 2 in the middle, we choose the left one. Otherwise, we could do a right bias, and we could prefer that one. Doesn't matter but once you choose, you must always be the same. Let me stick to the right bias. If we're right biased, what it means is when a node has too many values, you line up all the values, you choose the one in the middle that's on the right. Okay, in this case, that's this number, the 13. All right. Now, given that value, you're going to have a left child, which is the 11 and 12, and a right child, which is the number 14. And this number we propagate up. So what this will now become is the number 10, the number 13 here, with the right child being 14, and then this one being 11, 12. And this is still to the left of 10. That's the update. Okay? Let me go through that again. We want to insert 11. 11 would go into this child. I'm trying to go back. All right. Well, whatever. 11 would go into this right child, but now there's too many values. So we're right biased. We're going to choose the 13, and the 13 is going to become a parent. And then there's going to be two children. There's going to be left children, which are the numbers to the right or to the left of 13. And there's going to be a right child, which are numbers to the right of 13. And 13 is going to become a parent. So here, because we have room above, 13 is going to take that space. 13 has its right child, the things that were bigger than it. 13 has its left child, the things that were less than it, and 10 stays the same. Things that were to the left of 10 remain to the left of 10. Things that were to the right of the 10 remain to the right of the 10. And we're good now. That is still a biased, that's still a balanced tree. We're done. What if there were already 3 values in the top node, like say a 7 between the 5 and the 10? Very good question. Very good question. I have given you everything that there is to know about how to do this. And in fact, this next question about how would you insert 11? We just worked through that. Now let's insert the number 9. That's an even better question. Well, with where we're at now, that's a very good question, because you know that the 9 should go here in this place, but that's already full. And so it's going to have this propagation thing. And if we try to push it up, well, that's full too. And what happens? So I'd be happy to walk through this with you. I'm going to ask first if there's some brave person who would like to give it a go.
I could try.
Very good. Very good. All right. So we're inserting 9.
I just put it in the chat, but I think you would have to. I don't know if you can do this, but I think you would have to take the 10 out of the top and put it into that third child, and then put a 9 where the 10 originally was.
Yeah. Let's see. That would be a way to do it, but without going into the details, that is okay. How to say? That would work in this particular case, but if you can touch fewer parts of the tree, that's better. Because if you need to, first start here and go down to this part of the tree, and maybe things propagate back up. And in the meantime, you're going down a separate part of the tree to keep other things, like you're going down too many paths of a tree. So it can work. It can work. It might even, at a large scale, be efficient. That I'd have to think through. But there's another way to do this. So let's go step by step through it. First, insert 9. That's what we want to do. Let me turn off my video. What do we do? Insert 9. What's step 1? Whoever was just talking, I'm sorry, was that, I think you inserted 9. Yeah.
That was me.
Yeah, good. Mueller, yeah. Huh?
I'm honestly not too sure.
Okay. So we start here, right? We always start at the root. Always with a tree, you start at the root. So which path do we follow?
After the 5.
After the 5. Very good. All right, because 9 is between 5 and 10, so we go here. We want to insert the number 9. I'm just going to write it here. But that wouldn't work because that's too many numbers. So how do we go from here?
Could you? I don't know how to do it in less steps. I keep thinking of things like putting the 13 in the 4th child and then moving the, like, I can't think of how to do it in like less steps.
Okay, so let's here we are now. That's where we would put 9. And so we take the middle numbers, these two, and we've decided that we're going to be right biased. So that means that of the 2 middle numbers, we're going to push the 8 up. Okay? So let's go through that. So we're gonna make a little bit of a mess of things, but everything will work out. So we put the 8 up. The 8 would go there. And then we're going to have children to the left. That's the 6 and the 7. Space those out a little bit more. And then you're going to have a 9 here. That's bigger than 8. All right. Okay. So now that these children are so far so good, but now this number 8, now this node has too many children. And so we need to now propagate again. We need to break this one up. And so this now has 4 numbers. Of the 2, we're right biased. So we make the 10, we move it up. There's the 10. And now this is going to have 5 and 8 as left children. It's going to have a 13 as a right child. And that's fixed. There we go. Done. So no node, we're dealing with m equals 4. Do any children, is there anybody who exceeds 4 children here? No. Can we make the tree any shallower? Can we have any fewer than 3 levels? Here's level 0, level 1, level 2. Could we have just 1 level? No. So the tree is balanced. It's still an M tree. And that's our update rule. It's the same update rule all the time. Put the value as low as it can possibly go in the tree. If you break things, because a particular node has too many values, you break up the node. In this case, we're right biased, so we take the right middle value, push it up the tree. If there's room in the node above it, like when we inserted the number 11, and we had to push up the number 13, great. then you end there. But now when we wanted to insert the number 9, not only did we have to break up nodes, and then we had to push the 8 up, but now pushing the 8 up made that node too full, and so we had to break it up and add another layer above. That's what building it from the bottom up means. You put it at the bottom, you might break things, but in the process of fixing everything, you just push up, push up, push up, and maybe you create another level, which is what happened here. After we inserted the 11, and then we had to insert the 9, it was inserting the 9 that increased the depth of the tree. That had to happen by this procedure. In this way, the tree remains balanced and it remains as shallow as possible. And we can do an analysis on this to show that this algorithm is sane, that it works in all cases. That is all possible. But for this class, this isn't an algorithms class, all right? So we're not going to be going through that. I'm actually going through just the, on paper, this, that, okay, we're all good. To try to have you internally be okay that things work out. You don't have to be able to explain step by step by step how they work out, but you must be convinced that things do work out. That's the point of this lecture, okay? The details for binary trees, know them. The details for other variants of trees, including B trees, B plus trees that we're talking about today, don't worry about the details. Well, if you're interested, fine, but I'm not asking questions about the details. It won't appear on any exam or anything else. But it is very important to me that you know that the details exist and that you're convinced of them. If you were so inclined, you could look on the web or you could ask somebody to go through the details, and you're fully equipped to do that. I would do that for you guys now, except this isn't that deep of a course, okay? This is not an algorithms course. This is a combination of now talking about a more involved data structure and a more involved algorithm where the details aren't the point of this. The point is that it's a tree that remains balanced, and you can have more children than 2. And so long you have those things, trees are super nice. We like trees. You should know why we like trees. You can search fast, you can insert fast, you can delete fast. That's why we even talk about trees ever. It's because of those 3 benefits that we have. Here happens to be a more involved tree. So long you're convinced that things work out, I'm not lying to you, and that you can do fast search, fast insert, fast delete. That's what I care about you knowing about. What's the difference between the square and the circles? I'm sorry, there is no difference. I'm just being dumb and not being consistent myself. I'll make them circles. There's no difference, yeah. Okay. Okay, very good. What else do I want to get to? Very good. Let me pause here and ask if there's any questions about this idea of a B tree. It's different than a binary tree. some really good questions. I mean, whoever is asking those, like thinking steps ahead of really putting somebody into a tight spot as far as edge cases, that's excellent. I mean, I'm so proud of you for being able to uh, put those forth. I mean, you're doing my job for me. We have another homework on this before the exam. No. The exam next week. Are there multiple right answers or only one? I don't know exactly what that means. Let me answer these in order. So, yeah, no homework before the exam. The exam will be next week. I'm thinking Tuesday. So I want to release the exam at the same time for both of the sessions that I'm teaching, and you guys, we meet on Tuesday. So I'll be releasing the exam, I think, for you guys on Tuesday. No surprise. For my other section, where we meet Mondays, Thursdays, they will have the midterm released on a Tuesday, which is a little bit odd for them. But, you know, I mean, because everything's kind of electronic now, and I'm not monitoring anybody taking the exam or anything like that, it makes it slightly easier for me to give everybody who I'm teaching the exam at the same time, to collect the exam at the same time. That's really the reason why I'm doing it that way. So expect it next Tuesday. I would have liked to give another homework, just so you know more about how I ask questions. But at least you've had one. I'm Given the fact that I want to have an exam next Tuesday, I feel uncomfortable giving another homework. At least something that will be graded. I'll try to give out some like practice problems or something like that. You know, something where you can still work on stuff, you can still practice, but nothing that is going to be graded. So I'll probably do that this week. Next week will be the actual midterm. And yeah, I mean, next week, you know, class time, we're not taking up. I'm not administering an exam during class, although the exam will be released next Tuesday. We're going to just have regular class on Tuesday. So I'll just be continuing all of that. As far as the material, expect basically everything that we've covered before the release of the exam. So that will include all of the background, all of the fundamentals that we've talked about. Maybe on Friday when we shift gears into a new topic, I might ask like one question about that, but it would be nothing involved. But if I've introduced new material, that's fair game. I mean, I'm not going to be a dick about it or anything. Like I'm gonna, you know, it'll be an appropriate question on new material. How long will you have to complete the exam? You will have between 24 and 36 hours. So I'm going to release the exam. I'm not sure if I'm going to do it before this class or after this class, but it'll be due at like Wednesday at 11:59 p.m. Something like that. So you'll have all of Wednesday plus whatever extra time on Tuesday. If I release it in the morning, you'll have that extra time. If I release it in the afternoon, whatever, you'll have somewhere between 24 and 36 hours for it. Which I'm designing the exam such that I think that if you were to study for it, and you print it out or whatever, it would take you the amount of class time to work through, where you have your cup of coffee, you sit down at your desk, and you should be able to get through it with your mind focused in like an hour and 20 minutes. Uninterrupted, but like, yeah, real focus for an hour and 20 minutes, and you should be able to finish it then. But I'm not watching you do it. You happen to have more time for it. But that's the way I'm designing the exam. The questions would be similar to something like a homework. I'll try to give some practice problems just to give you guys a little bit more experience and maybe what to expect as far as the questions I ask. Okay. Let's move on. I want to go back up here real quick. Where I'm sorry, it's so messy. But here, this idea. Actually, I'll turn the camera on. All right. So I want to take a moment and focus on this concept, which I talked about the last class. That you have a bunch of data stored in, I don't know, call it a table. It's fine. And then separately, you have something we're calling an index table. And the index table is the data structure. That's where we spend time to build it. And it also takes up a little bit more space. Now, the data that you're storing, there's no order. If there is any order, it's just by accident. But you want to insert more data. You want to delete data. All of that's very fast. You don't need to organize the data. Okay? And the reason why that's fast is because we're using pointers on the index side. So anything you want to index, you can find by following a pointer to the data. Let's take this number 23 here. Student with the ID 23, they happen to be at index 2. I can follow it. There we go. I find Mary. She has the student ID in 23. Maybe I didn't mention this detail of it the last class, but certainly we set things up the last class. So here, all right, I'll spend a little bit of time on this because it's this is a nice feature. We talked about two ways of encoding a tree. One way was layer by layer, and that works. And I don't want to annoy you, but you can kind of forget about that one, the layer by layer thing. I know we spent time on it. The reason for that is because I think that it gets the point across more quickly of how you can take a tree and put it inside of an array. And that is a conceptual step that I think comes across easier when you consider something layer by layer. The second method that we talked about is using pointers. And for all intents and purposes, the layer by layer method, the pointer method, they're basically the same. I mean, it's the edge cases where one might take up more space than the other and stuff. But the pointer method is the better one because you can build on it. There's benefits to that method in particular that other methods use, in particular B trees, B plus trees, and everything else. They're actually using pointers. They're not doing it layer by layer. I didn't go over the index table.
Yeah, Professor, I don't remember seeing this table. If you scroll a bit up on
Yeah.
on the notes, I think we went. Yeah, this is probably where we ended. Yeah, this is most likely where we ended, where
Oh.
it says the pointer array and the value pointers.
Now it's making sense. I was teaching the other section yesterday, and I really felt that in that section we went through this index table. And I was scrolling through the notes, and I'm like, I don't see it. Did I not go over this? I remember very clearly. I thought that we covered this. So apparently, for my other class, I accidentally opened up this notebook and started teaching them, and I didn't teach you this stuff. So, boy, all right. Now I know what's happening. Let's go through this very quickly. All right. So, we have a bunch of data. We're storing the data on a hard drive like this, all right? This type of hard drive, not this one, all right? That's too small because it costs money to make things smaller. And great, you'll spend money to make it small to fit in your laptop. But when you're storing a bunch of data, you can take up some space, all right? You can have like a room full of computers. And so you'll use a bigger hard drive because you can fit more stuff for cheaper. This is where the data is going to be stored. In addition, you're going to store a little small file called an index file. That small file, once the computer boots up and stuff, it's small enough that you can copy it to RAM. Now you have your data structure on RAM, which is like 1,000,000 times faster. And not only is RAM 1,000,000 times faster, but you're also using a data structure like a tree. And we like trees because you can insert, search, delete very quickly everything on a tree. So you boot up the computer, you take the time to take the index off the hard drive, load it into memory. Now you use the data structure in memory to quickly figure out where the hell on the disk is the record that you're interested in finding. Like this disk could hold 1,000,000 students. You want to find a particular student right now. So you don't want to start at the beginning of the disk and slow from the beginning to the end. Not like that. Instead, you have your data structure loaded into fast RAM. In addition to that, the data structure allows you to find the location of the student that you care about on the disk. All right, so that's how it goes. Now, here on the right, we have a table where, I'm just, imagine it as a table. It doesn't really matter, but imagine it as a table. That's our data on students. We have a student ID, we have a name, the student address, maybe their phone number. And these things, each of them, they take up some space. Okay? So the student ID, let's take 16 bytes for that. Okay, so a byte is 8 bits. You can store a student ID in 16 bytes. That's enough to store however many numbers are required for the student ID. Maybe you use less, but in any case, you're reserving 16 bytes for the student ID. Names, a little bit longer. My name, Nathaniel Reed Pinkerton Hobbs. Nobody should have a name that's that long, but that's a long name. And so let's reserve 64 bytes for the name. The address is, let's call it 32 bytes. And a phone number, let's call that 16 bytes. Okay? So those are each of these columns. The student ID, 16 bytes, the name, 64 bytes, an address, 32 bytes, a phone number, 16 bytes. Which means 16 bytes plus 64 bytes plus 32 bytes plus 16 bytes would make one row 128 bytes. Feel free to check my math. I don't care. That's the amount of one row. Oh, dude. Sorry, there's something else that's actually pretty important here. Did I talk? Let me actually switch to these other notes. Did I go through this with you guys? This image?
No.
No. Okay, very good. All right, so we have to do that. I'll just stick to these notes, same thing. All right. All right. Data's going on this. This is called a hard drive, also called a hard disk. The disk is a good name because inside of this are disks, like here drawn on the screen. Okay, so it's a, I might show a video about what this looks like on the inside. Boy, all right. So we have a disk. Okay, it's like I think you guys know what a record is, like like that you listen to music on a record. And a record has tracks. Track 1, track 2, track 3, track 4, like that. And if you ever played a record, you know that there's a needle that goes somewhere on the record, and then the record spins, and the needle goes over it. And the first song, the first track starts on the outside, and then as you continue to play the album, the needle will move more and more and more inside of the record. So on the outside is maybe track 1, like on this picture. That's the first song. And then more towards the middle is track 2. That's the second song. And then track 3, it's the third song, and stuff like that. So we have a disc, and there's these things called tracks that are on the outside. Or also if you're running track, right, on like a track, everybody has their own lane and whatever. That's this outside kind of circular thing called a track. In addition, there's something called a sector. And the sector is this thing in blue here. Now I'm coloring it in purple. This is another way of taking a disk and making pieces of it. Okay, one way is with tracks that go circular. Another way is, what if we look at it like a pizza pie, and we're cutting slices of a pizza. Hey, there's your slice. That's another slice. We cut the thing in slices. All right, that's another way of breaking up a disk. And those pizza pie slices are called sectors. So we have tracks and sectors. Now, if we have both tracks and sectors, then we can start to talk about specific pieces, like this one in green here. That's called a block. That's the intersection between a track and a sector. Okay, I've colored it in green here. You can see it. That's a block. And this particular block, the green block, is track 2. So like it's the round thing. You can verify it's track 2. And sector 3, it's the third pizza pie slice. Okay. Now with both a track and a sector, you get what's called a block. Now that's the most small unit of measurement in a disk. It's called a block. Okay, you measure time, the smallest unit is a second. All right, you measure distance, maybe the smallest unit is a millimeter or a centimeter or like a 32nd of an inch, whatever. There's like the smallest unit that you can talk about things of. For disks like this, the smallest unit is called a block. And a block is defined in exactly the way that I just said. It's a pair of a track and a sector. Now that block has a certain size. It depends on the hard disk, but 512 bytes is pretty standard. Okay, so that's 2 to the 9th, 512 bytes. You don't need to know the number, doesn't matter. I'm just being specific for fun. Okay, so each of these blocks on the hard disk are 512 bytes. Now, let me jump back to this. All right. So here we have a table. Each row of the table is 128 bytes. 16 bytes for the student ID, plus 64 bytes for the name, plus 32 bytes for the address, plus 16 bytes for the phone number. Add them all up, you have 124. Let's assume that our disk has block sizes of 512. That means that on a single block, we can store 4 rows. 128 plus 128 plus 128 plus 128 equals 512. Okay, so that's highlighted in red. In fact, I kind of wrote it here. 4 rows, 512 bytes, 1 block. There's a little bit more I want to say about this, but we don't have that much time left. Okay. I'll just kind of wrap things up, I guess. We can pick it up the next class. We'll have a bit more of this to get through. I know I didn't talk about B plus trees, which is a slight extension on B trees. But we did we covered B trees. That's fine. This here, with the table, with an index table, this kind of thing, that's important to know. And the main idea is taking data structures which are nice on paper and understanding that the reason why we have them is because, like, we're dealing with hardware. Like, these are things that engineers build, really smart guys who have disks that with magnets that can store your ones and zeros, and you don't have to be a physicist to understand the high level of how disks work. And the smallest unit is called a block. Every time you read a hard drive, you will be returned a block. Let's say, for example, I only cared about this row, only that second, or row 1, whatever, index 1. I only care about that. If I ask for that record, the hard drive is going to give me the entire block, this whole 4 block. That's the smallest size that a hard drive deals with. Because it's slow, it's going to read a block. If you need less than a block, throw out the other information that's returned to you. You got to spin this disk. You got to have the head go over and read information. And so the smallest thing is a block. Even if you want less than a block will be given to you. And for the sake of speed, in the real world, hard drives are slow. You want to read them as little as possible. So trying to come up with ways to make the number of blocks that you need to access as small as possible is the goal. Okay, that's the background. We're at 1:20. I'm not going to keep you guys. I'll stick around for any questions if you have them. Thanks. See you on Thursday.